Happy Thursday afternoon. We have to finish up implicit today, right? And then start related rates. Two physics people are missing. It's worrying. We actually did finish up with implicit. We're now looking at the logarithmic differentiation method and the inverse trig derivatives. So here we have a function 1 plus x to the 1 over x. This is not any of the functions we've studied. Right? It's not a power function. It's not an exponential. It's certainly not trig. It's certainly not logarithmic. It's not product, not quotient. So what we have to do is we have to say, okay, well, if this is true, then this is true. But laws of logarithms allows us to write that. Now we find dy dx. Right-hand side, left-hand side, sorry. Left-hand side is a simple log function. U prime over U. But the right-hand side is not a quotient. So we have to use quotient rule. Physics must have been rough. You need to go get coffee, huh? I was saying both my physics people are missing, which doesn't bode well. Physics test? Physics test? Oh, yeah, rough. Derivative natural log of 1 plus x. Just 1 over 1 plus x, right? Derivative of 1 plus x is just 1. So I'm going to write that just simply as x over 1 plus x minus just log of 1 plus x. Right? Derivative of x is 1. All over x squared. Simplify. top line? That's x over 1 plus x.
And why is the exponent not 1 over 1 plus x?
For the second line? Because I'm multiplying by the common denominator of 1 plus x to clear out. All right, so multiply every single term by the 1 plus x. This allows us to write just multiply by y. But what's y? Which we can rewrite. So you could write the exponent of 1 plus x as 1 over x minus 1, or write it as a single fraction. 1 minus x all over x. Doesn't matter. I think I'll keep it that way. There's your derivative. Again, that technique is known as logarithmic differentiation. And it is the only way to find the derivative of functions like that, function to a function. So again, take the natural log of both sides. So dy dx over y equals that right-hand side product, isn't it? Verify that's the derivative using the product rule. Common denominator. Multiply by y. But y was what? X to the sine x plus 2.
Above the derivative of the natural 1 of x was 1 over x.
It is.
What's that over, what's that over there?
Which term are you looking at?
That term to the right, in the middle there, natural 1 of x, power of x.
Here.
Yeah, that.
Common denominator. I multiplied this term by an x. And then using the laws, I can write as that. And actually, that's a good point, because I can also write that up there as well, right? I can write it just as x to the x cosine of x. I actually think I will do that, now that's pointed out. Write it that way instead. And then, of course, simplify. And there's the derivative. Again, not necessarily a difficult process in of itself. You just have to be comfortable with your laws, specifically the laws of logs. Inverse trig functions. What is the derivative of the inverse sine? Now do the general version. So close. You're missing a term. h prime of t. So what is u prime in this case? And what's u squared? Can that be simplified in any meaningful way? That's why I said meaningful. You're right, that is a difference of squares, but it serves no purpose to do that because it's not going to cancel with something in the numerator. So just leave it like that, not your derivative. Derivative of inverse secant. So there'd be our general rule for inverse secant. Same u, so same u prime. Can that be simplified? I am in such a good mood after last night. I'll give you a hint. Yeah, he knows. He knows why. It can be simplified. And not just that they lost; they got crushed. Absolute value of a product is the product of the absolute values. Right, so absolute value of 2t is the same as absolute value of 2 times absolute value of t, which is 2 absolute of t. No, I was just explaining why you could take it out. That's why. See, that's not good. You should know why you do things. That's what math is. It's not about what you do, it's why you do it. You're not wrong. You're actually not wrong. Math started as philosophy and then evolved into mathematics. Read some of the more historical math articles. Like read the original statement of the Pythagorean theorem, how Pythagoras stated it, and it's all philosophical. The statement and the proof are philosophical. Well, I mean, they are. Or not. So I'll say they're not as far off in the sense that of English and Spanish not being that far off. They're both a language with rules.
What's better?
Math. Math is, as far as I'm aware, the only language that doesn't have ambiguity. Ambiguity. So in English, I say there. Which one? There's three. But in math, if I say something, there's only one because it has a specific definition. Now, if I give you a word, so if I give you a term in mathematics, it has one meaning and only one meaning. So, for instance, divisibility. That has a specific meaning in math, and there's only one. Or sometimes u squared plus 1. That order doesn't matter. G prime.
I'm going to go with 2.
And what is u squared?
4x squared.
Can that be simplified? There's your derivative. What kind of function are we dealing with?
Drawing the product.
All right, so product rule. What kind of function is the first function?
First one up there or the first one you wrote down?
No, on the original function.
Okay, well then the first one is a sine function.
What's its derivative?
Cosine to the same value as sine cosine. Yes, one second. Okay, that, yes.
Second function. Is what? That's the derivative. Right, so the second function is the inverse cosine, which has that derivative. Right, so now it's really a matter of, do you want to write this as a common denominator or not? Does it really benefit me to do so? Not really. Aside from that, can this be simplified? So now it's just rewriting it. No, you cannot. Because the inverse trig functions do not have the same identities.
Do they have their own separate identities?
As far as I'm aware, no. What kind of function are we dealing with? So we have to use quotient rule. Numerator, what is its derivative? Denominator, what is its derivative?
Negative 1 over the square root of 1 minus x squared.
All over inverse cosine squared. We can simplify. And that is about as far as we can go. Any questions on implicit differentiation? Good. We're done with derivatives. Now we have to apply them. So now we know what a derivative is and how to take them. Now let's use them. And one of the most common applications is known as a related rate.
Does this warrant its entire section in my notes? Like, my notes split into limits, derivatives.
This is now applications of derivatives.
Okay,
So it's a new unit. A related rates problem is one in which we are given a relation involving specific quantities and their rates of change. What is a rate of change?
wouldn't that just be the derivative of another function?
Rate of change is just a derivative. Now, oftentimes we are not explicitly given the relation. We have to figure that relation out. And that is generally the hardest part. Once you determine the relation, it's relatively simple. But like most applications, the hardest part is the setup. Water flows onto a flat surface at a rate of 5 cubic centimeters per second, forming a circular puddle 10 millimeters deep. We want to determine how fast the radius is growing at 3 values for the radius: 1 centimeter, 10 centimeters, and 100 centimeters. It is first generally good to list out what you know, so what you're given, and what you want to find. What do we know?
So we have units, we have centimeters, we have seconds.
Yeah, we'll deal with the units later.
Okay. What's on the flat surface? That rate.
So what values do we know? What is that? Of what? What else do we know? What other value are we given? Which is what? We'll go with depth. Same thing.
Yeah. We know the puddle is a circle, so we don't have to worry about the shape very much.
There's a problem. What is the problem? Well,
How much water
we
was
actually
started?
do.
Was there any water before it was starting to heat up?
That doesn't matter for purpose of this problem.
So we can just do those up before.
It doesn't matter. Whether there is or not is irrelevant. A physics person should know what the issue is. Yes, what about the units? The units are not the same. They have to be. So how do you want to fix it?
Centimeters are in the equation, so you probably need to convert our millimeters to centimeters.
That would be the easiest, but you don't have to. You could convert centimeters to millimeters if you wanted to. So how many centimeters is 10 millimeters? 1 centimeter. Yeah, it's a decimeter. But it's not used that often. What do we wish to find?
Well, no,
Speed of what?
growth is instantaneous speed of
Speed of what? Radius. More specifically, at some radius value. There's three of them. First, I'm going to write it as a function of some just arbitrary r naught, and then we'll go from there. Now we need the actual related rates itself. We want a relation for volume. I never said this was a cylinder. It clearly is, but I never said it was. So I'm going to derive the volume, not knowing it's a cylinder. Specifically, it's a right circular cylinder.
theoretically could be a
Volume has a specific definition. It's cross-sectional area times depth or height, whatever you want to call it. But the area, the cross-section is what? It's a circle. And what's the area of a circle? And there's your volume of a cylinder, a right circular cylinder. Now we want d dt of both sides. Volume with respect to time is what? I don't want a value, I just want, I guess, the rule. So just take the derivative of the, ignore the value for right now. Remember, trying to write it as a relation. Now we want the derivative of the right-hand side. However, depth is constant for this problem. So you don't need that part. And I can simplify it even further because we know the depth is 1 centimeter. So actually, I can just get rid of that from there too. There is our related rate. At this point, you have two options. First is to now plug in your values and then solve. Second option is to solve for the quantity you want to find and then plug in your values. I typically go the algebraic route, which is the latter. But the VBT is a constant. For dVdt, it was given to us in the problem. Right, it says it's flowing onto a surface at a rate of 5 cubic centimeters per second. So when R is 1 centimeter, what is dRdt? Physics friend, what's missing? What are the units?
Centimeters cubed in the numerator, or centimeters cubed divided by seconds. Cube divided by radius, which is in centimeters. If I'm not mistaken, it should be centimeters squared.
Centimeters per second. There's a 1 centimeter in the denominator as well for the depth.
I thought that was a constant.
It is, it's a constant 1 centimeter. I got rid of it here because it's 1. But it is still technically there.
Could we also,
Right, so technically it's that.
could we also reason that out by radius being kind of a one-dimensional?
That's
So like circumference.
how you would typically do it. Right. Remember, depth is just 1 centimeter. So your denominator technically is centimeter squared. Right. R is being measured in centimeters and D is being measured in centimeters. Right?
What if the since it's a constant, what if it came up with a
Well, the derivative is a product. It's a constant multiple. So that d would still be there. That d is right here. Right, the derivative is 2 pi r d d r dt. Because even if you treat d as a variable function, that would still be product rule, which means you still have that d in there, right? So think of, when you do the derivative, the pi and the d is your constant multiple. Remember what constant multiple rule says? So it'd be pi d times the derivative of r squared. So that d doesn't disappear. The other way, and this is how I typically look at it, is you just look at what is the rate of change, dr dt. What are the units of r? Units of t. So dr dt has units centimeters per second. And that's the dimensional analysis for a rate of change. You don't look convinced.
No, I just don't know why I didn't reason the fact that you know that purely by being a radius, it should just be like 7%.
Because you're focusing too hard on the dimensional analysis of this piece up here. You weren't even looking at the dr dt. You were just looking at, I'm assuming, you were just looking at the 5 over 2 pi r. Because that's what it sounded like. What about at 10 centimeters? And then 100 centimeters. As the radius gets larger, what's happening to the rate at which the radius grows? It's decreasing. Specifically, if you actually look at this, it's proportional to just 1 over r. 5 over 2 pi is a constant.
So it's proportional to
Yeah. So in this case, we have an inverse proportionality.
That doesn't mean we want to simplify our answer down to just 1 over r, right? Okay.
Now, remember what proportionality means.
I don't.
Two values are proportional if one's a scalar multiple of the other. Right, so in the case of dr dt being proportional to 1 over r, that means that dr dt is some constant times 1 over r. And in this case, that constant is 5 over 2 pi. Circular balloon. is inflated with air flowing at a rate of 10 cubic centimeters per second. How fast is the radius of the balloon increasing at the same three values? So we kind of have the same values here, don't we? All right, we know the rate of change of volume, 10 cubic centimeters per second. And we want the RDT at a value of the radius. What's the relation we're looking at? Is there something other than an actual answer?
Says a circular balloon, like the inflation has any cubic, and I know max is just a two-dimensional balloon, sphere or something.
Well, that's what's being asked. That's what I'm asking you.
The word circular here is really throwing me off. I don't know if it matters from real world physics.
Is there any other kind of physics?
What is that over there?
So it'd be non-real world physics? Or would that be imaginary physics?
I don't know.
I guess technically there's imaginary physics. It's just physics we make up. Or the physics as we wish it would be. That would be nice. So what is the relation we're looking at? You don't like this, oh boy, you're in for a lot of fun because this is still an easy related rates problem.
Why is it the word circular?
That's very important, by the way. Oh, that makes me sad. It's on the first day handout, the review of pre-calculus and the 4/3 pi r cubed. The reason circular is there is because a circular balloon inflates to a perfect sphere, which is why we can use that volume. If it wasn't circular, that would not be the volume. Right? So the typical balloons you think of are not really circular. They're kind of like that light bulb kind of shape. That doesn't have that as volume.
Yeah, I was just really thrown off because I thought if they were trying to go for a perfect sphere, they would say spherical. I thought there was more meaning.
That would give way too much.
Okay, all right.
Differentiate with respect to t. What do you get as a relation? So left-hand side becomes what? . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . What's the right-hand side?
4 pi r squared PRDT.
Again, we're trying to find the RDT, so I'm just going to go ahead and solve for it. dV dt is a constant. It's a constant 10, right? So it's what, 10 over 4, which is 5 over 2. Five over 2 pi r squared.
So dV dt is 10 over 2, right?
dV dt is just 10.
Oh, okay, I see how that got down.
What is dr dt when r is 1? Specifically 1 centimeter.
5 over 2 pi.
At 10 centimeters. Reduce that. At 100 centimeters. 5,000? It's 4,000. And I don't have enough room. Right, in this case, notice that our rate of change is inversely proportional to the square of the radius. Right, so this happens to be an inverse square relation. But this is where it now starts to get fun. And I most certainly do not have time to do this one today. So that is where we'll pick up and finish with related rates on Monday. So now we're going to have to draw pictures. We're now going to start drawing pictures.